Hello students, today we are going to start our third coding, that is 4-bit counter. This is little bit advanced from the previous code. There we used data flow modeling, here we are using behavioral modeling. For data flow modeling we used assign, and in the behavioral modeling we will be using always. So let's see the coding. Yeah, what is counter? A counter is a sequential digital circuit that counts clock pulses, updates only at clock edge, stores value using flip-flop. This is explanation. All these explanation we can go inside and see so that you will understand this explanation very clearly. Yeah, students, before entering into the code, I wanted to teach you few things so that it will be easy for you to understand the coding when I am writing. So now we are going for the 4-bit counter. The values from 0 to 15, that is in binary 0000, 0001, 0010, and it goes till 1111, that is 15. And then again, since it is counter, it again counts 0000. And here it has 16 states, and this is called mod 16 counter. And now the main thing which we are going to keep in the mind is, look at this. This is the counter working. So in this counter we have to keep in mind, if reset is equal to 1, the counter clears and it becomes 0. In this stage, reset is 1. Counter is clear. And then if reset is equal to 0, the counter starts its operation. That is, it increments by 1 and stores the value in the queue. Look at this. After reset is 0, it starts and increments by 1 in every steps. So this is the first point you have to keep in the mind. If reset is equal to 1, counter clears. If reset is equal to 0, the counter increments by 1. Yeah, students, next important thing you have to keep in mind is always that postage clock. That is, always is used for behavioral modeling, and postage clock means that when clock rises from 0 to 1, only the operation begins inside. For every clock edge rise, operation begins. And rich, it is used for storing the values, and we know that we use less than or equal to for non-blocking assignment. We should not use equal to, and q plus 1 is increment logic. So you keep all these in mind, and next I am going to show you one tabular column. If you're understanding that tabular column clearly, then we can start our code writing. Yeah, students, first I'll explain you this table so that it will be clearer for you to write the code. First thing is clockish. It is very important. Only when there is clockish, the operation begins. And then the reset. We know that if it is the reset is 1, it will clear everything. And if reset is 0, the counter operation begins. Here we will see what the operation is going, and here we will see what happens in the counter. So the first thing is initial stage. The reset is 1. In the initial stage, no clock pulse is applied. So nothing operation is taking place. It is just going on. Then the first clock pulse is applied. The clock rises from 0 to 1. The clock is applied. And initially, if we want to start an operation, we need to reset everything. We need to clear everything. So we are giving 1 as reset. After giving it, everything will be clear. See, it is 0000. So first we are clearing everything. After that, we need to perform the operation. So to perform the operation, the second clock pulse begins. When the second clock pulse rises from 0 to 1, to perform the operation, we can't keep the reset in the 1. So the reset 0 is given. When the reset 0 is given, the counter starts its operation. Let us look at here. It increments by 1. So the value from 0, 0, 0, 0, it is incremented to 0, 0, 0, 1. And we need to continue this operation. That is, if we want to continue this operation, if we do the reset one, it will clear everything again. So we have to keep the reset in 0 and we need to continue the operation. So to continue, the third clock cycle is applied and then reset is at 0 and it increments. The same way for the next clock, reset is in 0, it increments. Similarly, it will be incrementing for all the stages. Look at here, the final 16th stage, we are getting 1111. After completing this, the next cycle begins. See, it started beginning 0001. Sorry, 0000, then 0001. It keeps on continuing until we are stopping or we are giving particular time to stop the operation. You can ask, ma'am, if this reset is given as 1 in the 5th stage, what happens? Let us see it. See, in the 5th stage, instead of 0, I am giving the reset as 1. So what it does, it clears everything. See, it is cleared. And in the 6th cycle, we have to give the reset to 0 and start the operation. It starts from the beginning and it performs the operation. It performs the cycle. So the reset, 1 is for clearing and 0 is for continuing the operation. All these are performed when the clock cycle, it moves from 0 to 1. Yes, students, now we are going to start our RTL coding for the 4-bit counter. The first thing we have to do is we have to give the module. Obviously, after the module, we need to give our module name. Our module name is counter underscore 4-bit. This name, as I told, you can give any name, then opening the bracket. After opening the bracket, what we want to do? We have to give the inputs and outputs. Here the inputs are clock, reset, and we have 4-bit output. So we need to give the inputs and outputs inside this. So let's, next input clock is given. We know that clock means clock signal. Clock is like a heartbeat of the digital circuit. Every time clock rises from 0 to 1, something happens. Without clock, nothing changes. Okay. Then the next input we are using is reset. We know what the reset does. If reset is 1, it clears everything. And if reset is 0, counter counts normally. Next we are assigning the output. In this 0 to 3 we have used because it is 4-bit output. So it can store the value from 0000 to 1111. So we are using this. And this Q is the name of the signal. I have used here Q. We can use any name. And next one, why we are using this reg means because in counter the values changes on clock edge. So it must store the values. For that reg is used. Now we have assigned all the inputs and outputs and we are going to close the bracket. The next one is very important. The always is, we know it is for behavioral modeling. And then the post edge clock, when the clock rises from 0 to 1, the operation begins. The operation doesn't begin continuously or it is not randomly. Only at clock edge it starts the operation. So when the clock rising from 0 to 1, start the operation. Let us see what the operation is. If reset. In this if reset, if this reset is equal to 1, if S, what it does? It clears everything. Look at this. Here in this Q, we know the name given to the signal, and less than or equal to is for non-blocking assignment, and 4-bit. This B is for binary, and 0000. Now the condition is reset is equal to 1. If reset is equal to 1, clear it. So the counter becomes 0000. Else, if reset is not equal to 1, if it is 0, what happens? The counter, it increments by 1 and value is stored in Q. This is the counter operation. After doing this, we are ending it. Yeah, we are ending the module, and this is the code of our RTL for 4-bit counter. Now we have written the RTL code. We need Testbench to simulate it and see whether it is correct or not. So in the Testbench, what all the things we are going to do is, we know that when the clock signal here rises from 0 to 1 only, our operation is performed. And for every operation of counter to increment, we need clock edge. So in the RTL Testbench, we will be telling that when this clock rises and at what time difference the clock will be rising, and then when we are giving the reset equal to 1, and after what time difference we are setting it for 0, and then we will tell how many counter increments will be doing and how long we will be performing the counter operation. All these we will be giving it in the Testbench. Yeah, this is the Testbench. The first thing we have to do is we have to give the module and we have to give the name for it. Mostly we give the name, whatever we have given in the module, we give the name and we put under TB for the Testbench. After giving this, what we have to do? We have to give our inputs and outputs. So we know that here we give the input using reg and output using wire. All these we have seen already in the previous classes. So the inputs, we are having inputs clock, reset, and the output we are having. So for the input we are giving reg, and the next input is reg reset, and the next is output. So we need to give wire. So we are giving the output wire. First, we have given the module name and given the inputs and outputs using reg and wire. After completing this first step, the next step what we need to do? We need to instantiate the design. Look at this. We need to instantiate. That is, we need to bring our code into this Testbench. So what we are going to do now? The first thing is we have to give the module name which we have given it in the RTL code. There we have given counter underscore 4-bit. That name we have to give here. And then UUT is unit underscore test. We know that it is instance name. And then opening the bracket. After opening the bracket, now we are connecting the Testbench to the counter. So this is our Testbench clock and this is a module port clock. So we are connecting it, and we are connecting the test bench reset to the counter reset. We are connecting the test bench queue to the counter queue. Close the instantiation. After closing this, the next operation what we are going to perform is, for the clock generation, we are going to write the code. Let's see what this clock generation is doing. Look at this. We know that to perform the counter operation in the postage clock, the clock must rise from 0 to 1. Only if clock edge is rising, we can perform the operation. So for all increment operations, we need the clock edge. We can't give it manually every time. So this will do that. That is, what it does means, for every 5 nanoseconds, it generates the clock signal and it provides the clock edge that is required for the counter to increment. Next, we are starting the initial begin. That is, we are making the clock 0 and we are making the reset 1, so that we are clearing everything and waiting for 20 nanoseconds, and then the reset is made 0. We are making the reset 0 to start the counter operation, and then here we are giving 300 nanosecond wait. Why we are giving this means, a clock period is equal to 10 nanosecond. So this 300 divided by 10 is equal to 30 clock cycles. This counter increments 30 times. So we are giving the value 300. We can give it 200, 100, how much ever we want to run, we can give it. So now here the counter increments 30 times. And then it is finishing the process, and we are ending the module. So this is our test bench. Let me summarize it. In this test bench, first we are giving the inputs and output values using reg and wire, and then we are instantiating our RTL code into this test bench, and then clock generation is done. After that, we are giving the initial values to perform the operation, and the total timing the counter must increment, and then we are finishing it. So we have completed the test bench. Students, next, to learn the next level advanced code, please subscribe our channel. Thank you.